Welcome to Dr. Powell in the book Discrete Perspectives in Mathematics. This is subsection 4.4.5. Okay, so we're going to be talking about associativity with this operation that we've been talking about, where we have an anchor at infinity, and we say a plus b is going to be, well, we look at the third intersection point, we go to a vertical partner, and that's it, a plus b. So is this operation associative? All right, we're going to use a fact as we move along. We're going to look first of all at an intersection proof type of idea. First of all, if we have three lines, that actually can be represented by a cubic type equation. Notice, so this is like y minus 2x. If that's set equal to 0, that's a line, right? It's an equation of a line, because that's like y equals 2x. Similarly for this one, similarly for this one. What if we multiply these together like this? Now, if we have an equation like this with this set equal to 0, that means this is 0 precisely when either this is 0, or this is 0, or this is 0. See these ors? The graph of this is actually the union of those three lines. The line that comes from setting this to 0, or the line that comes from setting this to 0, or the line that comes from setting this to 0. Which means anytime you draw three lines, you actually get something we'd call a cubic in x and y. A cubic equation in x and y represents any three lines straight lines that you draw. So now a cubic equation has the same type of feel as what we were dealing with finding third intersection points. Same ideas. If you find two, you can do a polynomial. You can replace things and then do a polynomial division and actually get a third intersection, which is with a multiplicity, which is kind of a neat idea, and that we can actually do that. And we'll see that a little bit later. But right now, let's take a look at what we need for associativity. So we want a plus b plus c to be the same as a plus quantity b plus c. So quantity a plus b first, and then quantity b plus c later, to see that these two things are equal. All right, in general, here's a little schematic of what we're trying to do. So a plus b is third point vertical. Okay, that's a plus b. And then if we want to add c to that, then we draw a line between that and c, and we find a third point of intersection, then we go to the vertical one to get what that is. Now, really, we're just going to end right here before we do the vertical. So we're just going to end right here, because if we go the other way and we end there, we would end up going to the same place. So if we're ending at the same place here with taking a vertical partner, we really will come to the same place before we take a vertical partner. So really we can just end on a third line. So for a plus b, we have two lines. And then for the last one, so a plus b, we have two lines. And then to add a c on, we'll just put one more. We'll just use one line. We won't do the last vertical line because we'll know that the two will be the same if they meet right before you take a vertical partner. Okay, so then thinking about the other one, what if we do b plus c first? So b plus c, so we add that, we go vertical, we get that. Then we draw a line through there and a, and hopefully we get to the same location. If we get to the same location, that means that indeed this operation is associative. So let's just kind of think for a minute about associativity. What if we don't have associativity? Then order really does matter. I mean, if we wanted to add a string of things, we'd have to first do a plus b, and then take that result, and then add c to it, then take that result and add d to it. And you couldn't do it any other way. Like, this would be a no-no. We wouldn't be able to do this. A plus b, do that, and then do c plus d, do that, and then put them together. We wouldn't be able to regroup. So this is, we really do need associativity in order for this operation to be nice and to be especially if we want this to be a group. Okay, so that's kind of what we're looking at. Now, All right, so we have the red lines for that and the blue lines for that. But we're going to take a look at this, and in the next subsection, we're going to discuss how you can use this in. So see how we have 6 lines and our cubic. We're going to take a grouping of 3 lines and another grouping of 3 lines, and those will be 2 cubics. And then we'll have this other the elliptic curve itself, we'll call it cubic. So we'll have like 3 cubics to work with. And we'll be looking at the intersections between 3 cubic equations, and making the characterization of, well, they must have a common endpoint. And that's going to be investigated in the next subsection. Thanks for watching.